Now it will be okay. Okay, last time, you remember that I defined what model checking is, or at least to do formal verification, specifically the model checking variety. You need, there are actually three components. One is you need a way to model the systems that you want to analyze, okay? That the particular formalism that we'll be using is called transition systems. Okay, that's the model. And then you need to have a way to say what specify the properties that specify, that is in the form of a property, your desired behavior of the model. Okay, for that, we will be using either specialized logic that can talk about the kind of properties that we want to verify, of the kind, a few things that I showed some examples of, or you can use automata, specialized automata, special purpose automata that is able to express constraints on the behavior. And then you will be devising or developing efficient algorithms to automatically check that the properties that you specify is satisfied by the model. Okay, so these are the three things that we will be discussing, will be covering in the course. Okay, and after introducing transition systems, we'll then go on to introduce a few logics, specifically two logics that we will primarily be using to specify the constraints on the behavior. And after that, we'll be talking about various ways to check that given a model and a set of properties, if the model satisfies the properties. So what I'm going to be talking today is models, okay? The transition system formalism as a formalism to formally model the kinds of systems that we want to analyze. So let me go to this. Yeah, this is the outline for the lecture. Yeah, this I've already said. Okay, so what kind of systems and properties? So recall that we want to model things like, a controller that controls the traffic signals at an intersection. Okay, and this is, or it can be, these kinds of systems can have a mixture of hardware and software in them, or it can be pure hardware systems like this, and you might want to verify that the counter, this is implementing a mod counter, okay, and its value is always less than or equal to 3, or it can be pure software, where you want to assert and verify that certain conditions always hold good when the control reaches that point in the program. Or it can even be concurrent programs, and you want to assert that there are no data races or deadlock and things like that. Um, yeah. So what does modeling entail? Okay, modeling is something, a model of a system should usually primarily uses abstraction. And abstraction means you omit some detail. Okay, let's suppose that you are talking about this hardware. Okay, in real life, the voltages, the currents, etc., which determine the behavior of the thing, will be a continuous variable. Okay, so here, and this is like what the transistor really behaves. But you usually you don't need to. Of course, at certain levels, you may want to actually poke, monitor the currents and the voltage and so on. But if you really want to analyze this system at a logical level, then you know that you don't need to track these things at this level of detail. You throw away the information about the actual current and the voltage values, as you know that if the voltage at a particular output, which is this chip here that I'm talking about, is above a certain value, then it is considered as one, logic one. And if it is below a certain value, it will be considered as the logic level 0. Okay. So that is one aspect that modeling does. You need to really understand what detail that you need to retain and what detail that you can throw away. And this process is called of retaining the relevant details while developing the model is called abstraction. Abstraction means you keep certain details and you throw away certain things. So, usually the first thing that you do is systems are in certain states. So you have to model the states, and the state, the system is in a set of states. Typically, for example, in order to model states, you have to model, you do it in terms of state variables. Okay. So, for example, what are the state variables? What would be the state variables for modeling a system like this? Can one of you guess?
The color of the present color.
What? Yeah, I mean the different the color of the lights. Okay, there are two signals here at the intersection for each of them. So each of them will represent variables, and each of them will be in either in. So you can have a variable. The state comprises of the kind of colors that each of these signals have, and which can range over red, yellow, or green. So here, what is relevant is the state of these two flip-flops. Okay, A and B, they can be in 1 or 0. How about for the software? Code.
Value of X and Y.
Yeah, the value of the variables. And there is another component that is very critical for program execution, which is the program counter also, okay, where you are at, correct? Because the change in the state very much depends on where you're at, because the program control can also change as you execute. So you're right, the values of all the variables, the program variables, as well as the location at which your currently your control lies. Yeah, I mean here in concurrent programming, you need to not only worry about these variables and the locations, since you can have multiple threads and therefore the schedule, I mean, that you actually use in the that determines which the order in which these threads are scheduled may also be relevant, or you may be able to model them without, regardless of the thing. And those are the kinds of things, okay, that you will have to determine. But yeah, particularly, you will have to determine what state variables that are relevant, and what is the set of values that those chosen state variables range over. Okay, so in this course, we assume that our state variables are discrete, in the sense they range over discrete sets, as opposed to continuous sets, okay, like real variables and so on. So we are interested in modeling and analyzing discrete systems. Okay. Of course, transition system formalism, which I'll be introducing, can also be used to model continuous systems, but that will not be the focus of our study in this course. And then you have to model state transitions, right? Because the kind of behavior, is that I'm talking about here. Traffic lights should never be green at the same time, which means there is already a time notion, okay? So because it evolves, the state of the system evolves over time, okay? And our behavior is the one that we want to model is not a static behavior, but dynamic behavior. So in this case, as time evolves, the states change. In this case, the color of lights. So here, the time is guided, for the hardware system, the time is guided by the clock. And as the clock ticks, that is the notion of time. Here, the value of all these registers, the value that the registers are holding changes, okay? And here for program, the time notion of time in a program may not be real time, as is the case here in the clock, but the notion of time, which corresponds to the transition. What is the notion of time when you are analyzing and modeling software? Any guess? So, yeah. So, for example, execution of an instruction. Okay. So you're executing one instruction at a time. So you're transitioning from. So it's at the level of each instruction that you're executing. In this case, it is the execution of a single basic statement. Okay. Here you execute this and you come here, and after that you execute this and you come to line 2 of the program, where you check whether, execution of statements and maybe checking of the conditions. These are the basic steps that correspond to time advance. Okay, so the notion of time can be very abstract. Okay, depending upon what the system is and at what level that you're modeling the thing at, and that is what is captured. So in any case, so you need to the states change with the state of the system changes with time, and the time. In some cases, maybe you can model it in real time, or you can abstract it and associate with a transition of the state of the system. Okay, and as I said, here also there's the question of the time can be continuous or discrete. Okay, and we will focus on discrete time transitions. Okay, we may not be talking about exact real time, in terms of seconds and minutes, but they will be abstracted abstracted into transitions, and it will be talked in terms of unit of time. Okay, an abstract unit of time which corresponds to a transition in the transition system, and we will be defining what it means for a transition. So let me come to the actual formal model that that we will be using. So what is a transition system? It's a three-tuple. Okay, it has a set of states, which itself is structured in terms of the values that a set of variables, chosen set of variables, can take. Okay, and then there is a set of initial states in which the system can start, from which the system can start operating. And then there is a transition relation, okay, which determines the when the system is in a given state, what the next possible states can be. This can be defined as a relation. Okay, and these are the three things that can capture. You need to capture the state. You need to capture the set of initial states that the system can start from, and how the state of the system evolves, and that is captured by the transition relation. So each transition here is the abstract unit of time over which the system evolves. Yeah. So is that clear? Any doubts or questions here?
Yes, sir, I have a question.
Yeah.
We will be studying only discrete time systems, and these systems will only change its states with respect to only time. It will not react to any external events. Right?
No, that is not true. So external events, environment is also very much a part of this, and we will see. So the transition system, the environment is also a part of it. But the assumption is that the the time transition is not continuous. See, you could describe it in terms of discrete, like these relations and so on. See, if it is something like a like, for example, I had this example of, did I show this? Okay. Okay, I had the example of the pendulum, no? Where was that? So let's take this, okay? Here, you can discretize it and then model it. There are two ways you can model this system. You can discretize it and then chose a certain, a discrete time, and then you can model the transition of, this system. Or you will have to, or you could choose to model it, as the time as well as the value, or as being continuous. Okay, in which case the mathematics in this kind of a transition system may not be adequate. Correct, because you will have to use use the the system in the limit. Okay, you have to plot theta over time, with the time itself is continuous. Then modeling the state transitions like a transition relation will not be adequate. Okay, you will have to use partial differential equations and calculus. That is the distinction that I'm making. Okay, you see the difference?
Yes.
So
sir.
yeah.
My doubt was I watched this a lecture like in logic automata and games. It was taken by Professor Narayan sir, and
Yeah.
he was introducing like a Bucci automata. I'm not taking
Bucci automaton. Bucci automaton, correct? Yeah, you've already taken that course, is it? So
no. I just watched it out of curiosity. I'm not taking this course this semester. Yeah, he gave an example at the start of his lecture. He described the lift system, which is also a discrete system, but that system reacts to external events like when a person presses the push button, the up button, the lift will come out. So it reacts to external environment.
Correct.
Here, the transition relation is only S cross S.
Yeah. No. But the thing is that there is a way. So this can encompass. Okay, we will get to an example, but to make it explicit, this doesn't preclude your thing from capturing the environment. Okay, you can include. A system can be open. So I never specified limited what components that you can choose to include as variables, or that is you can choose to monitor. So the system environment is also inputs. Environment can be modeled as a set of inputs that that are coming from the environment. Okay, now that environment can be changing at its at its own set of rules. So if I include the inputs that can change as per the rules that the environment encompasses, that also is part of the system. So you can always include both the environment as well as the actual system which is reacting to the environment, the signals or the inputs that are coming from the environment as part of the state variables. So in which case, you will be able to model that as well. Okay, and you will see that I understand the kind of doubt that you might have. How do you model the environment? The environment can change at will. Okay, and the system is responding to the environment, and therefore there is this notion. So two points I'm making. I'm not precluding inclusion of the components of the environment in the state as components within the state. Okay, and the way that we do that is by including that as part of the state. And there is a notion that we will be using called non-determinism, okay, which comes convenient for modeling the environment. Okay, so bear with me, and that you will see how that can be done. Now, there are several ways to model environment, but what I'm saying is this way of modeling does not preclude including the environment as part of your system, so that you can talk about it always as a closed system with the environment. Okay.
Okay.
I also had a doubt. I think it's similar to this. So like the transition relation says which is the next state to go from a state, right?
Correct.
So like when to go, does it say when to go, like at what condition it should go from one state to the next?
Yeah. All that will be part. What condition, etc., will be part of the part of this definition of T. But this transition itself time will not be talked about in an explicit way. Okay. But if you want, so the transition itself will be advancement of time. Okay. the transition itself will be the addressable. In that sense, time is abstracted out. Okay, so the transition corresponds to this says how from a current state what are the conditions under what conditions you go to a particular next state. Okay, and the assumption is that the transition will be abstracting the notion of time. Okay, and that's how you model. Now you are at will to choose the granularity of your transition system. In other words, you're at liberty to choose at what level you want to model the transition. Okay, so let's get to the example. So since the choice of the variables to include a state and the granularity at which you want to define this transition relation is your choice, you can model time at whatever granularity as you want. Okay, but we will not be talking about real time. That is the only distinction. If you want to include that also in terms of clock, and then you want to do, you can include that as part of your state as well. Okay, but usually you don't need to. Okay, and the transition itself will be, for example, I can include a timer. Okay, a discrete timer as part of as a state variable, and it keeps changing. It just keeps counting from 0 to 1 to 2, 3, and so on. Okay, but it may not be that you may want to do if you want to model at that level where you want to also analyze maybe performance of how long it takes things and so on. So you could do that, but as you will see, it makes sense to abstract the time also, and but yet retain the notion of at the granularity at which you want to abstract the time and into these transition relations. So these are all very good questions. Okay, and hopefully it should become clear as we as I'll introduce these examples. Okay, so here, okay, first I will take this example. Okay, so this a code is a piece of code. Okay, that's a syntactic representation. So you've heard of control flow graphs as representation for programs, flow charts, haven't you? Okay. You have, I presume, right?
So this is just similar to flowcharts.
Yes.
Yeah. So what I have on the right side is what I call as control flow graph. Okay. Yeah, and this is another way to do. So this itself is a different representation of the thing. So I start with there is only, so here what I'm modeling is what does a transition here correspond to? Okay, so it corresponds to so the program that I've chosen on the left side shows instruction by instruction. Okay, so here the first transition from the initial state corresponds to executing 0 and 1 instructions, the statements at 0 and 1, and then I have completely abstracted this transition here corresponds to execution of the body of the loop as a single thing. Now, so you could be modeling this. So I've already chosen the granularity thing. So here the time is not real time, but rather the time as we observed before can correspond to execution, the time for each instruction. That's one way to model. Okay, or you could, in which case you will require I told you that you need the location, in terms of go to and so on. If I model it like this at this level, then I'm abstracting away. So each transition now corresponds to my own choice of what a block of execution is. So here I'm choosing to model the initial block. The initialization block is one transition, and the body as another transition. Okay, this is still very much a modeling of the behavior of the thing. So these kinds of different level of representation for program we already use, even without talking about the dynamic behavior. So here, program is a syntactic representation, is a finite representation of a program whose dynamic behavior can be infinite. Correct. So here still I'm talking about not transition systems, but rather just representation of the program, and how the representation of program itself gives you a choice of your the granularity of the transitions and the time that you have. So what I have as a transition system is something that captures the dynamic behavior. Okay, and here I really want to make a distinction between program as a syntactic object and this particular control flow graph as a representation of the program, as opposed to what I call as transition system. Okay, so the transition system is something that captures the behavior of the program. So what could be a transition system corresponding to this program that is described at this level? So here your system variables, as you said, was the variables that X and Y range over. Okay, so your initial state is the state where X is equal to 0 and Y is equal to 0. Okay, and your transition here corresponds to the execution of the body. Okay, of the thing. So the transition corresponds to the entire execution of the body of the program. So you could, that's what this transition corresponds to. So it says if you're in 0, 0, you would go to 1, 2. If you're in 1, 2, you would go to X gets incremented modulo 3. So X goes to from 0 to 1, 1 to 2, and after that it goes back to 0. So Y is whatever X is. It is X plus 1. Okay. Therefore, this is what it means to model the behavior of the execution of a program as a transition system. So specifically, so more formally, so what are the choice that we have? My model has a set of states, okay, and a set of states is captured as X and variables ranging over X and X, Y. Okay, so it has two state variables, X, Y, and that's why it is being modeled as a cross product of D1 and D2. Okay, so D1 is the domain over which X ranges. D2 is the domain over which Y ranges, and here they happen to be D1 takes value and X takes values from 0, 1, and 2. 0, 1, whereas Y can go from 0 to 3. The initial state is captured by this tuple 0, 0. So since there are two variables, I'm using a tuple, correct? Okay, and then R is a relation, okay, which exactly says what the what the values are, and what the when you're in a particular state, what it what the next state should be. So if it is, if you're in a state 0, 0, the next state will be 1, 2. If it is 0, 1, your next state will be 1, 2, and so on. Here I've chosen to enumerate it, okay, just to illustrate what a transition system is. So this is one way of modeling, which corresponds to, I would say, the control flow graph, at this as shown here. Okay, so here, what does a transition, one transition correspond to?
It's 0 to 1. State 0.
Yeah, execution of the body of the loop, once. Okay, so see, you have fair amount of freedom here. Okay, in terms of what you want to include as components of the state, and at what level of granularity, how, depending upon how you define your transition relation, you can also capture the granularity of time. Okay. Of course, yeah, in this case, there are this is okay. So from these initial states, these are the only possible values that X and Y take. Okay, but potentially when you just, okay, it so happens that in this case these are the only possible values that they can take. But of course, X and Y, there are also other. I mean, here I ended up guessing that this is what it is, and I chose those domain. But in general, you won't be able to do. How do you decide on a suitable domain for states? Okay, so they must be big enough to cover all possible, system states. So here I was clever. Okay, so I knew what the system was, and and somehow I guessed that these things. So I was cheating. Here. So there is this thing of how you choose the, in addition to this variables that you choose to include in the state, you also have to make a choice of the range of the domain. Okay. So, but how do you choose that? That you will have to, it must be big enough to cover all system states. It doesn't have to be precise, because you won't know. I mean, it's like choosing the domain to include exactly the states that they can reach is like putting the cart before the the horse, the cart before the horse. Okay, so that's why you're saying is your choice of domain should only be should be big enough to cover all system states, even if it includes some states that you may never reach. That is okay. Okay. So in other words, so if I can choose in this case natural numbers as the domain over which X and Y ranges, because that's how programs are in this case written, right? So if I choose it like that, then of course this is not a complete characterization, correct? Because there are states that, I'm assuming if I choose D1 and D2 to be NAT, then there are other states that are not shown here. Am I right?
Yes, sir.
Yeah. So, but that is not in some sense relevant, because they're not reachable part, but you won't know it in advance. That's why. So if you were using, what am I doing? Okay. So here it is. So, here I will change. Okay. So this is, this is better. Okay. So here, so if I make it as NAT, then my system will have also actually an infinite number of states, correct?
Yes, sir.
Yes.
Yeah, so it has all these white states in addition to the yellow states, but these but my initial state is still this, okay? The yellow states represent the reachable part of my reachable states, and all these things are they're not, they're not reachable, okay? So, but since I've defined it on NAT, my transition relation will have to be defined on the entire set of, over the entire domain, entire set of states. Therefore, so although they may not be reachable, so you will end up including them, okay? And that's how you model. So the model of the lesson, the point that I'm trying to say is that there is this, when you model, you have to choose the domain also, and the domain you can choose to be big enough so that it includes all the things. And the way that, and in this case, since you know that it can be any natural number, then and your transition relation has to be defined so that it is defined for all potentially possible states that your system can be in, and that's how that you define. Okay.
Sir, here,
yeah.
Like the state 30 does not have another state transition from it, right?
No, it does. Why not? So the transition. Okay. So then I have to say how you will define. Suppose I define the transition relation. So here, read it as D1 and D2 being NAT. Okay. So as I said, the transition relation has to be defined for every possible state. Okay. So I am defining, as I can see, if it is, so I'm defining it as same thing as mod. Okay. So from if x is equal to 3, it'll go back to mod. Okay. So I see that's how I'm defining the transition relation R has to be defined as a total relation. It has to be defined for every element, every state that is included in S. Therefore, indeed, there is a next state to this one also, as is shown by this transition. So if I do x is modified, x is modified to take on x plus 1 mod 3. So this from x is equal to 3, I will go here. And if y is equal to 0, I will go to 1 plus 2, correct?
But in this program, we have already initialized it to 0. X is equal to
that may be so. That's why I'm saying we'll have to, when you choose the domain to include other states, you better define the transition relation, since you cannot predict ahead of time. So you can choose your domain and you define your transition relation has to be defined for every possible thing, for every possible element in the domain of the state. So in that sense, you are defining it for all possible states, but your system, only some subset of the states might be reachable from your initial state. Okay, that's all.
Yeah.
That's all that I got. Yeah, you're right. What you said is correct. So, but so only a subset of the states are reachable. So, what is reachable is also part of your is something that you'll have to analyze. Yes, the way that I did it before that's why I said it was cheating. Okay, so that is not in reality. You won't be able to predict the reachable set of states, and therefore the way that you can do, just like they do in program, is you choose a range for the state variables that you know are big enough to cover all your possible states, and therefore but you have the just like how did you define? Ignore the initial state, okay, that is here. But in the body of the program, how did you define your relation? It never assumed the initial state. It was defined for an arbitrary value of x, isn't it? Yeah.
Yes. Inside the loop.
Yeah.
It's
Inside the loop, that is true. So this happens to be the initial state. Okay, this block that preceded the loop defined what the initial state was, but the body, the transition that corresponds to the body of the loop was defined for an arbitrary thing, correct? Okay, and that's what I'm doing here as well. Yeah. Did you get it?
yes.
Yeah. So in your question, yes, there is a transition. That's why I'm insisting that when you extend the domain, whatever the domain that you choose for the variables, that determines the universe, the set of all possible states that the system can potentially be in. Okay, and your transition relation will have to be defined on all of them. I mean, it has to be total over the entire state. Okay, so that's how that. So in that sense, it has to be in the transition system has to define it for all possible states in the universe of states, which is determined by the domain of the the variables that you choose. As a matter of fact, and because you allow this thing, that is where the model checking problem gets interesting. Your analysis problem gets interesting, because when you want to prove certain properties, okay, so for this program, the property is that x is always between 0 and 3, okay? I'm sorry, x is less than 3. X is never, x is always less than 3. So that is a property that this one satisfies. Okay, so as a matter of fact, regardless of what location you're in, x is always, the value of x is always less than 3, and that happens because you happen to start from a particular initial state, and although your transition relation is defined more generally, the reachable in all your reachable states, x happens to be less than 3, and that's because these things are really not reachable at all from a given state. Okay, so that will be part of your analysis thing. Now, okay, one more question that I have, that I want to raise is, so since we are allowing for infinite things, how can you capture? Obviously, if you define your model over infinite states, then your transition system will also have infinite states, correct?
Yes.
Do you agree? Yeah. So how will you capture this? See, in the case of program, you will, you need an infinite representation, okay, to capture this. I mean, if you did it in graphical form, where every bubble here corresponds to a particular instance of a state in the universe of states, then of course you will have you will need your graph will be infinite. Okay, right? Okay, first thing that I want to draw your attention to, do you see that what we have defined as a transition system is different from your control flow graph?
Yes.
Yeah. What way?
Yes.
Yeah. In what way is it different?
Like the states are, particularly the states are different, right? So here it's
Correct.
0 and 1.
Yeah.
And the
That's right. So
transition
here
stuff is
you're only modeling the location. Really, you're modeling only the location. Okay. And so it's a completely different beast. Okay. So here it's just a different representation of your program. So whereas a transition system is specifically introduced to model the actual unfolding, the dynamic behavior, okay, of your program, So here it captures actually not only the states that your program as can be in, and also the evolution of the states that your program can be in over time. Okay, so you see, so that is, since the idea, the goal of formal verification and model checking is to analyze the dynamic behavior. That's why we have chosen these things. So the states, so just don't get confused by the bubble here. The bubble in a circle here in the CFG, corresponds to locations actually in your program. Although I have thrown away some locations here, and I'm keeping track of only the initial location and the head of the loop. Here I am. Here the bubble represents actual each state that your program can be in, starting from the initial states, and that's why you will now have a conundrum. Okay, so since your states can be very large, even if not infinite, it can be very large. In a real C program, there's nothing like infinite. Okay, they're all ranging over some finite bit vectors. But even so, whereas if you treat the range as NAT, as I've done here, they are really infinite. So how can you even represent such transition system, and then let alone do analysis over that? Is a question, correct? Okay, it's a relevant question, isn't it? Yeah. So what do you think is the answer? I'm going to give you the answer in the next slide, but
maybe the reachable states will be finite. I don't know.
That is that's a good point. But the reachable state also may not be finite.
Yeah.
Okay?
It can also be very large. Yeah.
It can be very large, number one. But your system, your transition relation could be such that even the reachable set of states can be infinite. Okay, that's where logic and automata comes into play. Okay, so formulas, you remember that if you can view set of states as formulas. Okay, suppose I have, say, x greater than 0. Okay, x greater than 3, greater than or equal to 3. Okay, that kind of captures, if you view x greater than or equal to 3 is a formula, right, in propositional logic. That's why you remember that in the last class, I made the observation that, look, you can view the set of, a formula as denoting the set of states for which it is true. Okay, so the logical formulas give you, if you view it that way, then the whole set of infinite states can be, even infinite states can be captured by formulas which are finite. So x greater than 3 can be, if you denote as, if you use formulas to denote set of states, then you can, and you view the set of the set of states that a formula denotes as the set of valuations for which it is true, then you have a finite representation. The formula can be a finite representation of infinite set of states. Okay, that is the trick that that we use. Okay, this is what to a symbolic representation of a transition system. What I showed you here was a graphical representation, and that's why R was kind of enumerated as an infinite set, and then I raised the question, how do you even represent these things? Because if you want to develop algorithms to analyze these things, you have to find a finite representation. Okay, that finite representation can be either logic, you can represent these things as formulas, transition system using formulas, or they can be certain kinds of automata. Okay, Buki automata is one such finite representation of such transition systems. Okay, so those are the two things. You can either use logic, okay, logical formulas to represent the transition relation. So then you can get around this thing of, you'll have, that's a classical finite representation of infinite objects, or automata can be that tool as well, artifact as well. Okay, so in this course, first I will talk about the use of logic, specifically propositional logic. And then in the second part, we will talk about certain special kind of automata that can be used. So let's first about logic. So this is what I mean when I say symbolic representation of transitions system. So these you will see will be in terms of formulas in propositional logic. So this set 0, 2, 4, 6, 8, etc. can be represented by this formula in red here. X mod 2 is equal to 0. Okay, correct? So because every element that belongs to S is something that makes the formula in red to be true. Do you agree?
Yes, sir.
Yeah. So that is what the idea is. So you can use formulas in first order, first order formulas. In this case, X is ranging over numbers, but you get the drift, right? So if it is only finite set, then you can model using propositional propositional formulas. But nonetheless, this notion of modeling formulas, using formulas to model infinite states can be extended to something beyond propositional logic as well. So that is here, X is ranging over natural numbers. So similarly, for example, here 1, 2, so if it's a finite set, that can be done too, okay? Finite, but could be large, okay? So then you can use these kinds of, formulas constructed out of appropriately chosen predicates, okay? You can get even fancier, okay? So some sets, you can use the power of full first order predicate calculus, with the quantification, etc., to model very transition relations. After all, transition relation is also a set. Here I'm showing formulas to represent sets, but transition relation is just a set over the tuples. Okay, so similarly you can use formulas to characterize transition relation as well, because they are after all sets. Okay. So yeah.
The second example, why there is an X and it's an and symbol in the second.
In the second one, the and symbol. What about it?
It's X. It can be only X, right? Is the and necessary? Kind of
No.
Why and is there?
Why and is required? Because this one includes only those values between 1 and 10. Therefore, it is either x greater than or equal to 1 or x less than or
Okay,
equal to 2.
sorry.
That's what it
That's,
is.
Yeah, that's and of two conditions. I thought x and
Yeah,
x
and of two
was-
conditions. Correct. Sorry.
Yeah,
Yes.
yeah.
The-
Initially, I also thought like.
No. Yeah. I mean, yes. And it's not x and x. Okay. It is x greater than or equal to 1 and x less than or equal to 10. Okay. So there must be a parenthesis here and here. Yeah.
Yeah. Okay.
Yeah, just like you're free to use logical connectives in here, and you will, in general, you'll have to use it. Okay. So let's, so what are the things? So you have, going back to the thing. So S transition system, we will see. So a set of states, S is one particular state. And Sx, the value of some variables x in a state. Okay, so this is all well and good. So no, this is, so let me get to this. So T is a subset of, in the example that I'm saying, suppose it is n, two variables. Oh, there's only one variable here. Okay, so the transition relation maps, in this case, I'm using one variable. So T goes to, and if it's a single assignment statement, so then it is, a program with a single assignment statement, which increments x. The transition relation for that is this one, and can be captured by this relationship. Okay, so you will have the variable denoting the state, the pre-state before you executed the assignment, and prime x plus 1. Okay, so here I'm exactly stating the transition relation corresponding to the execution of the statement x gets x plus 1. Yeah. So using this idea, any question?
No, sir. No.
Yeah. Okay. So let's see how we could represent the transition system for the code example. So this is what I call as a symbolic representation. I'm sorry, this domain has to be NAT. Okay, there's a mistake here. This D1 is NAT cross S is NAT cross NAT. So initial state will now be a predicate. Okay, which is described by this formula. Okay, I'm using the notation. S has two variables in this case, X and Y. So that's why it is a tuple. State itself is a tuple. And S dot X and S dot Y are the two variables. So initial state is captured by this formula. Okay. And in this case, that set that is denoted by this formula happens to have exactly one element, but it is not necessary that it should have one element, because you can have systems that start with multiple initial states as well. Okay, and we'll get to that. So, and then your relation is now, because it is a transition relation, relates the pre-state to a post-state. Okay, and that's what. So it has to be a relation between two state variables. The post is denoted as generally we'll use the prime notation, and therefore your formula will now be will be stating constraints relating the primed variables to unprimed variables. So now you could capture this the transition shown here as S prime X is equal to S X plus 1 mod 3. And exactly, what is the expressions that are used here. Okay, and notice here that R has to be modeled as it has to be total. You will have to define it over all possible states that S that is included in S. Okay. So this is what I call a symbolic representation of the transition system. Although it can be infinite or very large, you can still represent them as you can use formulas as finite representation of those of the state. Yeah. Okay. Any questions here?
No.
No.
Okay, so I will go on till I'll take another maybe 5-10 minutes. Yeah. Okay. So there is another notion that we will introduce, non-determinism. This kind of addresses the question that you had about the environment. Okay, whether you will, how exactly can you use, can you include environment as part of the state? But this notion of non-determinism is very crucial in our modeling mechanism in formalism, because it can be not only used to model environment, but it can be used to throw away certain irrelevant details in your thing. There can be two kinds of non-determinism. So initial non-determinism, where initial state need not be unique, okay? And inputs, the environment in the inputs can change arbitrarily, okay? So you will see how that can be captured when you include environment as part of your state component. You need to deal with this aspect of environment. It can change, arbitrarily, or this non-determinism can, when you use it inside the definition of transition relation, it can capture. You can throw away the details about the scheduler in the case of concurrent systems by making a state to have multiple successor states. Okay. Now let me go to this system here. Oh, okay. So here, for example, suppose I want to model this system for arbitrary initial states. Okay, so I will do so. So I've removed the initial the code that initializes this. Okay, so this is wrong. Okay, so here, if I throw away that, everything can be the program can start in arbitrary initial state. Okay, so I should have removed this initial arrow here. Okay, so every state can be an initial state. You can even start with this state. Okay, so how do you capture? That is what this thing is saying. So S naught of S is now, I define it as true. True is something denotes the entire set. True is true of every possible state, right? Therefore, it includes the entire, tuple of that to that. Is that clear?
Yes, sir.
Yeah. Okay. So this itself gives you certain non-determinism, in the sense that your initial state can be multiple things, and that's the way that you capture. So in this case, your actual any state can be an initial state. You can start from that, but once you get to the yellow portion, you will stay within the yellow portion. So that is the that is the way that this thing behaves. So that is one way. So okay, I think I'm coming to the end of the thing. So maybe I will not get, because I will run out of my time. So let's so I will stop here unless you have other questions. So this, I will use this example to show you how to say, this is an example. Okay, I will just introduce you a little bit. This is an example. You see, whereas the previous example, there was no real inputs. Whereas here, this is a system where it is taking reset as an input. Okay. So you could say reset is part of the environment. Okay. We are throwing away the clock because, I'm abstracting it into transition. So the system changes. I'm assuming in synchronous systems, everything, including the environment changes the time, at the rate of the clock. And once the environment changes, the system responds. Okay. So therefore, so the notion of time, we're only interested in, you can throw away the clock and you don't have to have it as a explicit input because the transition takes that. But now we'll have to model reset. Okay. Now the reset also can be modeled as a part of the state. The state can now be viewed as having three components: A, B, which are the storage elements of this hardware, and reset can also be a state. I mean, which is part of the environment, can be a state. So now I've defined the delta defines what A and B are, okay, as a function of the current state, A, B, and RST. But what about RST itself? Okay, I mean, you will have to model. There's one input. So if you just model, of course, I mean, the next state here is dependent on the current state of the flip-flops as well as reset. But you will have to model reset as well. Okay. So normally what people do is they, you could use maybe input as a separate entity in your formalism and capture the next state that way. Okay. You can either have a reset when you're in a given state, which is corresponds to A, B. You can either you can have a transition for the case where reset is true, or the case where reset is false. So each of them will have two kinds of transitions, and you can label the transition. Okay, but we have not provided that capability in our definition of transition system. Instead, what I can do is include reset also as part of the state. Okay, and I will allow reset to change non-deterministically. Okay, whereas A and B are guided, are defined in terms of reset and the original value of A and B. As you can see, each from state, this is the initial state with 0, 0, and 0. So the reset component of the state can either non-deterministically go to 0 or 1. So each state here has two potential successor states. Okay, one in which the reset, which models the environment, can be either 0 or 1. So the transition relation is non-deterministic. I refer to this situation. This transition relation is non-deterministic in the sense that the successor state, I mean, to a particular state can be, it can have, a state can have multiple successor states. In this case, I'm using that non-determinism to model that the reset in the environment can change arbitrarily. Okay, it can flip to, it can stay the same, or it can flip to 1. Okay, and the notion of time is actually a removed clock, and it is the rate at which the notion of time is the rate at which the environment changes. Okay, every time the environment changes, something happens. Okay, and the environment itself in this case can change non-deterministically. Or if your environment is more constrained, you can use the rules of how the environment, the state variables that are part of the environment change. If it is doing in a constrained fashion, that can also be included as part of your transition relation. Yeah. So think about this. So it is in this sense I'm saying that the formalism of transition system, the way that we have introduced, is quite adequate. It is expressive enough to capture the environment as well by including the environment as part of the state, and then using non-determinism to allow for the possibility of that the environment can change arbitrarily. Okay, so I'm just contrasting. Sometimes people use this method, which is more compact, okay, where you label the transitions. But what I'm saying is that this labeling is not needed. You could include it as part of the state and allow for multiple successor states. Okay, so this is where I want to end today's lecture. Okay, unless you have any specific questions about this. Yeah. So does that answer your question? I don't know who asked the question about the environment.
I asked
Parmalai. Yeah. So this is how you do. So you can include it, but what happens is then in that case, you have to also include as part of the transition relation the rules as to how the environment changes. Yeah. Yeah. So, or you can have two systems. We'll see. Ideally, this is the way that I have shown here is making this open system that I've shown here closed by including the environment also as part of the system. Okay. But ideally, what you want to have is you want a system which is independent of the environment, and you want to have a separate transition system for the environment and have a mechanism to compose these transition systems. That is what we will be doing. Okay, how you compose transition system is something that I will talk about in the next class or the class after that. We will be talking about that because this is not a very modular way of doing it. But what I'm saying is you can, in principle, if you choose to do it, include the environment as part of your state and then model the complete closed system, the system that you have and your environment as part of it. When you do that, what I'm saying is that is like a closed system. So there's no inputs here. Okay, and there are ways that you can actually have environment and I think a separate thing and then compose as well. Okay, so yeah, the point I'm making is in principle the transition system formalism that we have, although it does not have inputs, is expressive enough to capture.
Hello?
Sir, your audio.
Yeah, I think your audio broke.
Oh, can you hear me now?
Yeah, now.
I think my internet connection is a bit unstable, it says. Okay, so this is a good point, to stop. Okay, And where did I will stop sharing. So, and I will